Alright, so this is section 6.2, which is on diagonalization of matrices. So let's recall an example from the previous section. So matrix is 5, 7, -2, -4, -4. It has two eigenvalues. First one is 3, second one is -2, and they correspond to eigenvectors. First one is 7, -2, and the second one is 1, -1. So by definition, this means a times 7, -2 equals to 3 times 7, -2, and a times 1, -1 equals to -2 times 1, -1. So if we put the two eigenvectors together as a matrix, then A times the matrix with the first column being the first eigenvector and the second column being the second eigenvector. So this is V1, this is V2. So this is A times first column is V1, second column is V2. By the definition of matrix multiplication, this is equal to first column is AV1, second column is AV2. And because V1 and V2 are eigenvectors, so AV1 is equal to lambda 1 V1, which is 3 V1, and AV2 is -2 lambda 2 V2, which is -2 V2. And if you check, this is equal to V1 V2 times a diagonal matrix with the first entry is 3, second entry is -2. Alright, so let's give these things names. So these are the same matrix, both first column V1, second column V2. Let's call this P. And let's call this D because this is a diagonal matrix. Then we have an equation which tells you A times P equals to P times D equals to P times D. And if we want to multiply P inverse on both sides on the right, then we know P and P inverse together is the identity matrix, which is just 1 technically. So we get A equals to P D P inverse. And remember, P is this matrix, and D is a diagonal matrix. So this is called the diagonalization of A. Alright, so let's we have seen an example. Let's introduce a few definitions. Okay. So we say if A and B are n by n matrices, then A and B are similar if A equals to P times A times P. Oh, sorry. A equals to P inverse for an invertible n by n matrix P. Okay, so notice that this definition is commutative. Because if A equals to P times B times P inverse, this means if we multiply P inverse and P on both sides, if we multiply P inverse on the left and P on the right on both sides, then these two cancel, so we get B equals to P inverse AP, which is equal to P inverse A. P is its inverse is inverse, so this is P inverse inverse. So this is equal to Q times K times Q inverse. So where Q is P inverse. Okay, so this note is telling you that A and B are similar, is equivalent to B and A are similar. So we don't have to worry about the order when we talk about two matrices being similar, because the order doesn't matter based on this notice above. Okay. Okay, so remember before we had A equals to P times D times P inverse, the diagonalization. Then the diagonalization of A means that A and a diagonal matrix are similar. Okay, so let's recall another example from the previous section. So recall this example. A is 3, 0, 0, negative 4, 6, 2, 16, negative 15, negative 5. So it's a 3 by 3 matrix. We have 3 eigenvalues. First one's 3, second one is 1, third one is, our first one is 0, wait, second one is 1, third one is 3, and the 3 eigenvectors are 0, 1, negative 3, and 0, 2, negative 5, and 1, 0, 2. So using a similar logic from before, we can write A equals to PD, P inverse. So P is the matrix with columns being the eigenvectors. So in this case, this will be 0, 1, negative 3, 0, 2, negative 5, 1, 0, 2. And D is the diagonal matrix with diagonal entries being the eigenvalues corresponding to the eigenvectors. So lambda 1, lambda 2, lambda 3. So this is equal to 0, 1, 3, the rest being 0. Okay. Right, so A is equal to this matrix P times D times P inverse. So this is the diagonalization of A.